Hello, hello, hi, hello, okay, can you hear me? Wait, can you, yes, thank you, Kimberly, okay, thank you, and thank you, okay, and can someone just make, it doesn't have to be Kimberly, can someone make a sound so I can know that I can hear you?
Hi.
Thank you very much. Okay, thank you. All right, here we are. Another madcap adventure. Hopefully you guys can see the board. Okay, sorry. Hopefully you can see the board, and the board is. Ooh, is that? Yes, the board. Hopefully that you can see. Hopefully is a quick encapsulation of the two equations that we derived last Wednesday. Um, um, we're going to do, today we're going to do one more practice problem altogether. It's actually drawn from the homework. So if you have been doing the homework and you will get points for having done that, you'll also have an easier time in class today if you've done this. But if you haven't, then you'll still be able to do this problem today because it's just based on everything we've done so far. And it's taken from the homework, but it's taken out of order sort of on purpose. So anyway, what I'm saying is we're still all just trying to work together to get what we get out of physics. And what we had thus far before last Wednesday was we had 5 equations. I'm saying, and equations are just statements, they're ideas, they're concepts, they're specifically either definitions or discoveries. And we had 5 equations that encapsulated the sum total of what we knew. The first 4 were definitions, right? We had definition of instantaneous velocity and a definition of average velocity, a definition of instantaneous acceleration and a definition of average acceleration. And then finally, we had this one equation, which I'm going to write again. Well, we finally got this one. So I'm on the second page now. We finally got this 5th equation. Again, we had 4 others that I haven't rewritten right here. We've written them a million times. I'm going to keep writing them a million times, but I haven't written them here. But based on those 4 equations, which were all definitions. So they weren't saying anything about the experimental world. They were just saying what words meant. And those words were velocity and acceleration. We then came along and said, okay, acceleration is a change in velocity. Velocity is a change in position per time. I should always say per time. So let me say that again. Acceleration is a change of velocity as time passes. Velocity is a change in position as time passes. So acceleration is a change in position as time passes, right? So if you're thinking calculus terms, which gets to be a better and better thing to do throughout physics, if you're thinking in calculus terms, we're just defining acceleration to be the second derivative of position with respect to time. Acceleration is like derivative number 2. Then we went into the real world, so to speak, in lab 3, just summarizing here. And in lab 3, we said, aha, it seems that in the outside world of space and time, or at least on the surface of the Earth, it seems like when things free fall, they actually do change their position and they do change their velocity. So they have an acceleration, but they don't seem to change that. When things fall, they seem to be changing on a level of derivative number 2. Not 1, not 3, but 2. Like that's the discovery. That's the point of like free fall numbers. Okay, I'm just summarizing where we've been in case whatever. So then we said, okay, from here on in cases, cases like gravity are so prevalent and so important and so easy to measure and stuff, cases of constant acceleration, that there's analytical things we can say about constant acceleration. And the first thing we said was equation 5. Notice 5 is our first not triple equal sign equation. Of all of our equations, it's our first one that is not just saying this word means that word. In other words, it's our first one that could ever actually even be right or wrong. This first equation here, this equation number 5, I'm looking at, oops, sorry. This equation number 5 in the middle of the page. That's the very first thing we've ever said in physics, literally, that actually could even be right or wrong. Everything else is by definition right because everything else was just by definition. This one says if acceleration is a constant, if you are changing your velocity, but you're not changing your change, then you can say, then and only then, you can say that the average velocity for some interval is the average of the velocities for that interval. It's exactly what we started the year by saying you couldn't always assume, and you can. Oh, sorry. Is that sorry? I'm just trying to review this. The other class asked me for more sense of context, so I'm trying to give a little more context here. But then we were going to get to, but if I'm boring the bejeebers out of everybody, we will get to the problem in a second. I'm just trying to summarize where we've been, which is to say that at the beginning of the year, we browbeat ourselves into saying average velocity is not defined to be the average of velocities. Like you can't assume, and you can't assume that the average velocity for an interval is necessarily the average of a couple of velocities that describe that interval. That's what happened in the whole like hill figure thing. Like you go up the hill at 40, you go down the hill at 60, but your average velocity for that whole thing is not 50, right? That was it. But then, surprise, surprise, what we're saying now is, okay, but there are conditions. You can't assume that the conditions are always this special, but there are special conditions where the average velocity is the average of the velocities. That is what equation number 5 is really saying. It's super powerful and super slippery, again, because it isn't always true. But when it's true, it's the thing that you really need to crack open the safe. So when and only when acceleration is a constant, we said average velocity is in fact equal to the average of the first and last, or the lowest and highest velocities, like literally add them together, divide by 2. A quick note on that. Once we said that, okay, that's where we were like Monday and Wednesday of last week, and particularly in this section, which has been a little bit more, a little less damaged by the clock. We are saying that under certain conditions, average velocity equals the average of the velocities. Whenever that is true, we were able to use that equation to algebraically combine it with the other we had, and we came up with equation 6 and equation 7. Like what I just now, what I'm trying to tell you is, please notice that equation 6 and 7, which we derived last week and which we're going to start using now, or start practicing now and then move on. But equations 6 and 7, which are the last of our kinematics equations, the reason and even though some of you may have seen one of them before, the reason we couldn't get them until then is they're literally just the algebraic manipulation or reconfiguration of the other equations that we already had. That's why we believe these, because they're just a rehash of old information. But that's why we also have to recognize there's no new information in 6 and 7. In 6 and 7, hold on a second. In 6 and 7, there is no new info. But that's why they're not controversial. But why they're necessary, why they're not useless, is because they are shortcuts. They are shortcuts to solving problems, depending on what kind of information is given to us in those problems. And you're going to see in the problem today, like equation 7 is 4 cases where time is not given to us, but we're also not solving for time. Then we use that equation and believe it, because it is just like it's just like doing 2 equations in advance without spending that time before you even plug in the numbers. That's why we believe 6 and 7, and we're going to use them. But what I want you to see, the way they're organized on this page, is since they follow algebraically from equation 5, 1, and 2, they are also only true when A equals A naught. This whole unit that, by the way, we're about to actually finish, this whole first unit of physics, if you were to try to find it in a textbook or in Google or whatever, this whole unit is sometimes called 1D kinematics, 1D motion, but it's also sometimes called the study of the constant acceleration equations, or constant acceleration, because all of this assumes that. I know I keep saying it and I feel bad in a way about that, but I also feel bad for everybody who doesn't hear it. This is all constant acceleration. This 6 and 7 are the last of the constant acceleration equations. No more are needed. After this, we go on to the next topic, but let's practice these. Okay, so I'm yammering. Let's practice these with, I'm going to give you a problem that's for today that we're all going to do. It has 2 parts. I'm going to try the same thing I tried in the other class, and it totally failed. So I'm just going to try the exact same thing again, because that's scientific. I'm going to try to not go in the breakout rooms because that's been annoying some people sometimes. I want to mix it up. We're not going to go in the breakout rooms, but I'm going to turn the page. I'm going to show you the problem that we have that has two parts that I want everybody to solve. I can't even see you right now. What I'd like everybody is to really try to solve these now in this time. Like, I'm going to shut up. I'm going to give everybody quiet time. What I first would like is the minute you've either hit a wall or have a question or are done, have answers and want to see what's what, then put an electronic hand up is what I'm going to say. I can't even see myself. I cannot see what's happening here. Wait, but in gallery view, why? Oh, I see. Okay. So I'm going to say you all, and you can talk. Like, I love the talking, which is why I like the breakout rooms, but I don't, but anyway, I want you all to work on these problems that I'm about to show you. My first request is that as soon as you hit any kind of wall, like you're done and you want me to talk, then put up an electronic hand so I don't waste everybody's time. We don't just sit there. But after a while, I may say, put up a hand now if actively you need more time thinking, because it's too easy to just lose everybody to like go out to lunch. I mean, which is where the breakout rooms serve a purpose. In other words, here's the problem. Okay, folks, here's the problem I want you all to work on. The given is, so it's this next page. I forgot I have to. The given is nothing new at all. The given is V naught of 0, like object starts from rest. We've been talking about that a lot. And falls near the surface of the earth, so it accelerates at a constant rate. Like, we're going to assume, as we keep doing, that we're going to assume in this problem that A is whatever it was at the beginning, that A equals A naught, never changes. And whatever that number is, we call G. Now, I'm going to say it's 22 here. Now, let me just be clear about something. We've been working with, it is the takeaway of lab, it is ever since lab 3, we are supposed to be comfortable in this class that there's a concept of constant acceleration, and that on the surface of the earth, there's actually a number for that if you're in the metric system. And the number is about 9.8, or what we call 10 meters per second squared. Like, I do want people to be used to the fact that that is the number, even though we totally will give it to you on the exam and all that. But recognize, okay, it's just a number. Like here's the number. It's approximately 9.81 meters per second squared, but that's approximate. That is chopping off digits that go on forever without repeat. So we could, as long as we're choosing how many significant digits to go to, we can just as legitimately call it 10. And I know I said this last time, 10 meters per second squared, but I do want to make it clear. I see this constant is so important, but what is important about it is its constancy, not the actual number. So I want you to take the thing of lowercase g super seriously, but I want you to be flexible about its size. Like, don't get bogged down in the 10 part. So recognize you could just as easily call it 32 feet per second squared. And that puts it in perspective for some people who are more American, like, units in their thinking, that, right, you can call it 32 feet per second squared. You can also recognize that, like, if you go to the moon, okay, this same phenomenon of gravity happens. But sure, the moon, it turns out, exerts less gravity on all of us. We would weigh less on the moon. And on the moon, the number's not 10, it's more like 1.16. So, of course, you should be able to solve problems whether you're on the moon or on the earth. It's the same type of problems, just a different number. But now, that's all true. I could today just give you another practice gravity problem and just say, let's do it on the moon with a different number, or Jupiter, where gravity is like 70 meters per second squared. But what actually we're doing is we're going to stay on Earth. I want to be very clear. What I'm saying in this problem that we're doing today is let G equal 22 miles per hour per second. Okay. Now, in fact, this is an earthly number. This is just one way to express the 32 or the 9.8. This number is correct. This is Earth. But it's expressed in it's expressed the way I expressed the very first acceleration we ever looked at in, like, one of the homework examples with a Toyota Corolla or some kind of car. I'm saying that this is a way to understand gravity that for some of us will help us understand acceleration better. And for others of us will give us an appropriate challenge in this problem we're about to do. I'm saying when you drop something, what you got to understand what acceleration means is if you drop something from rest, okay, and just let it go, like, make sure you're standing on a very tall building and it's not very windy and you drop something heavy like a brick, okay? If you have lots and lots of room below your feet and you drop a brick and let it go, go 1 Mississippi. At the end of 1 Mississippi, that thing is going to be going 22 miles per hour. I mean, it's going to be going 9.8 meters per second, but does any of us know what that actually means? Many of us don't think that way. It's going to be going 9.8 meters per second. Yeah. It's going to be going 32 feet per second. Yeah. But what does that mean? It means 22 miles per hour. You do the unit conversion and you'll see within 1 second, if you drop a brick, it'll be going 22 miles per hour. Now, within the second, it'll be going 44 is what this means. And at the end of the third second, just 1 Mississippi, 2 Mississippi, 3 Mississippi, like you're standing on a tall building and you drop a penny and it's not very windy, or you drop a brick, a stone, 1 Mississippi, 2 Mississippi, 3 Mississippi. At the end of that 3 Mississippi, it's going to be going 66 miles per hour. That's just a unit conversion. I'm saying that's the 9.8 number, but instead of expressing it as meters per second squared, if we express it as miles per hour per second, which is just as legitimate. It doesn't sound scientific, but it actually maybe is more sensible. After you do the unit conversion, you'll see that something accelerates in free fall at 22 miles per hour per second. So in 3 seconds, it's automatically, a brick is already going like the interstate highway speed of 66. I don't know if that puts perspective or not, but it is true. It is true. And I'm saying I want to use that way of looking at the number today to make sure we really get this. So I'm saying in today's problem, assume, like here we are, this board, given that we drop something from rest, so like, like here we are, we're like standing on a large cliff and we drop something, rock or some kind of item, some kind of item, and we drop it from rest. I'm saying you can assume correctly on Earth that it will have an acceleration rate, which is always the same, and it'll be pointing down. It will point down at 22 miles per hour per second. And that, again, that's the same thing as 9.8, just with the units written in a different way. What I want to know from everybody, and I'm going to shut up momentarily, this is what you're all going to do individually, or you can talk about it or whatever, but please do it until you're done one way or the other. Is I want to know, A, at the end of 1 minute, how far has this thing fallen, this thing. So again, be careful. You can use any equation you want. You can use all the equations. You can think through the equations, like understand them and use English. Do whatever you want. But notice I'm saying something accelerates at a rate of 22 miles per hour every second. I want to know how far it's fallen within the first minute. I mean, I want to know in miles how far it's fallen at the first minute. So be careful, but there is an answer. I want the answer to that. And how far has this? Okay, that's the first question. And the second question is this. At the moment that it has fallen 22 miles, like whenever that is, but like you let this thing just go and go and go. And again, its acceleration rate is constant. So I'm assuming there's no like wind to mess it up and there's no ground that it's going to slam into. Like we just give a lot of space for this to work. Then I want to know if it's fallen long enough that we let it fall 22 miles. Like eventually it's going to fall 22 miles. Maybe that's in the first second. I don't know. I don't think so. But this thing is going to fall 22 miles. At that point, when it's fallen 22 miles, I want to know how fast it's going at that point. And okay, so both of these are figure outable with nothing else but the equations or the concepts we have. Like you definitely don't need anything else. There's many different ways to do either of these. There's faster ways, slower ways. I also didn't spell object correctly, sorry. But this is the problem that I want everybody working on like now, please. So could I get a show of hands? Is it, wait, could you just raise your electronic hand if it's clear what I'm asking you to do right now? Like, even if you don't know how, that was so fast, Kimberly, I appreciate it. Thank you. Asia, that is so fast, thank you. I know, thank you, Marissa, I totally appreciate it. And every time I say one of your, Rachel, Abby, yes, okay, Elizabeth, Abby, Rachel, thank you. I totally appreciate it. And I feel cheesy even saying your name, but I feel like at this point I should because it's a compliment. So yes, I'm asking everybody, just do these two problems. Again, I'll just kind of I'm also not going to break our room so that you can keep seeing the board for anybody who's tuning in and out or like going to the shower and back or whatever. Like this is the problem. Again, it will, even if you've thought of no physics at all, like you've tuned into nothing, you actually, with just the equations that are written down, you could begin to make a go of physics of trying out these problems right now, really. But if you've been with me for every single moment of the way, I think you'll discover an interesting thing or two with these two exercises. Like it is worth thinking about for everybody, and it's possible for everybody to think about it. So that's the question again. The question is, A is right here. I will just keep flipping back and forth so you can copy. This is B. I think the whole question I wrote together. Yes, this is the whole question as one right here. I'll leave it for all, but also like here are all the equations. This is all we know so far. Oh, and one other thing. All we know so far, but it actually is a lot, but all of physics consists thus far of those 7 equations and that empirical like finding. Those 7 equations about acceleration, and then that the acceleration is about 10 in free fall gravity. Okay, that's the core. So I'll keep flipping, but that's all you need to solve this problem. But the problem is this. So I'm gonna shut up. Well, no, I'm going to bother you all for one more second with a quick story. I'm going to start saying the names the way like if I ask for a show of hands and then like people start raising hands, I'm going to tell you, I'll apologize in advance. If I see like Melissa raise her hand, I'm going to say thank you, Melissa. And I know that's a little bit cheesy or maybe condescending or weird, but since I really don't want to call attention to people for like physics answers, because then people will be, my reactions might be different if the answer is right or wrong. And I don't want to do that to people. I'm from now on going to make a point of saying people's names when they just like even raise their hand when I ask them to, because I do want everybody to be doing that. And I will tell you all, again, I've been teaching for 27 years, but like never in a virus before. But I had already been teaching about a long time when my now 14-year-old son, oh God, Jesus, my 17-year-old son, when did that happen? Anyway, my 17-year-old son, he used to come to classes with me when he was like 8, like to college classes with me. He was like really small, and he would come to these physics classes, and he'd been doing it for a while. And one day I asked him, and then he was really young because he was about to start kindergarten finally. This my older kid was, and so we were getting all excited for kindergarten, and I said, well, what are you looking forward to? Like, what do you think, since you've been watching me in classes like for so long? What are you looking for in a kindergarten teacher? Like, what do you want her or him to do on the first day? What's the most important thing they could do that would get you to like care about the class and pay attention to class and like kindergarten? I mean, it was a weird thing for me to ask him, and I probably shouldn't have. But he didn't even think about it. If any of you are listening, this kindergarten kid turned to me after he'd watched a bunch of John Jay college classes, most of which I taught. He turned to me and said, "They got to know my name. They got to know my name. Know their names." He said that to me. So, and I want to know your names, but I don't, but it's so weird to know your names in this way that I'm just going to say right now, anytime anybody gives me a hand or anything, I'm going to like say their names to everybody and get everybody to know their names. That's what I'm going to do. And it's an automatic compliment and no one's being criticized. But anyway, so do this problem, A and B, and raise your hand or anything if you have a question or you have an answer or you're done. But this is the problem to the left. On the board. Okay, now we just.
Professor, really quickly, what's the word on the third line? The
Oh.
first one on the third line?
Fair enough. Thank you. By the way, wait, the word is thinking, and you're right, that's crazy. But thank you, whoever's that way, who's asking me? Thank you for, was that?
Heaven.
Oh, heaven. Oh, you're heaven. Okay. Thank you. Thank you.
No problem.
The expression "thank heaven" is really going to take on a lot of meaning in this class. But yes, it's thinking. So what I'm trying to write right here to everybody who isn't you or Billy or Erica, I'm saying I'm changing the rules to everybody now, just because I'm just changing the rules. I'm saying, please do raise your hand now, anybody and everybody. Please do raise your hand if you want more time. Like I'm saying there. So what it literally says on the board here is, as long as you are actually thinking about what this problem, oh my God, this doesn't say anything. It says, as long as you are actually thinking about this problem at whatever pace, then please raise electronic hand for more time. So I'm now changing the rules to everybody because I'm doing a control on the experiment, so to speak. Like anybody who's actually thinking about it at all, I definitely don't want to interrupt you in any way or say a right answer or anything. But I think some people like may be totally out to lunch. So I'm now saying, if you're thinking and want more time, please raise your electronic hand. And if not, okay, then I'm going to say, one second, please everybody bear with me a second. One second, everybody, sorry. Now I'm getting things in the chat. Okay, this is very good, actually. Okay, let me say something to you. Now I'm starting to get a couple things in the private chat, and I totally understand why they are private. So I'm totally not, I'm not going to like say who did whatever. But what I'm starting to get in the chat privately is like gentle indications from people that they think they have an answer, but like they're obviously not sure of it, or they think something's wrong with it, or they're afraid it's wrong. Like, and as I say, I'm getting multiple things down the chat, and first of all, I'm psyched, and I am going to make a big deal of this because I really think for me at this point, like, it's all about however any of us, certainly including me, can like really participate in this Zoom crazy class. So I've gotten like 3 private chats now or so, maybe more. And each one of them is totally fair, totally helpful. First of all, like, I'm glad I got the chat at all. Second of all, I totally even see why these people are doing it in private, even if ultimately maybe it'd be even better if we didn't. I totally get why they're doing it in private, and I totally respect it. And it's a common theme. What I'm learning in private is that people have answers, but they're not sure if they're right. Now, this tells me a lot, folks. Like, first of all, you got to know, I literally can't even know. Like, I don't care about videos or this or that, but like the reason I'll make a big freaking stinking deal of one thing that Heaven will say or one thing that Billy will say or something is like, we're so in the dark here. Like, at any given moment, you guys could literally be sweating bullets over something I said that was too hard, or you could be bored to tears over something I said that was too easy, or you could like be in another room in a fight with your brother. Like, and I'll be sitting there going like, how come you don't understand acceleration? Like, I literally do not know at any moment where anybody's mind is. And you probably don't know how much, like, as long as I know where it is, I can meet it. Like, I don't have an agenda for you people that you have to get to a certain exact place in physics by a certain amount of time. My agenda is we all have to get better at physics, like every day or whatever. We have to get better. And so when I get these indications in the chat that like people have answers, that's huge information to me that you've even gotten answers. Otherwise, I don't even know how stumped you are. And I respect that you guys don't want to share them unless you're sort of sure that they're right. And let me tell you, it is true that some people in the chat just told me they had an answer, but didn't tell me what it was. Fine. And so to some of them, I literally just told the right answer, because now I know that they tried something and I know that about them, and they don't want to spoil my image of them by saying a potentially wrong answer. Again, it wouldn't, but I get that. So I just gave them the right answer. So now they can privately know whether they're right or wrong. And I can privately know that they just like rocked something. What I'm saying to all of you is, the good news is it's true. A couple of the answers that were put in the chat actually were wrong or incomplete. So it makes me feel like I can do my job now by straightening them out with everybody. But really, really, so even if this works for me, even if it means that you guys have to use the private chat to tell me when you're done with the problem, and like that's as far as you want to go, is to tell me that you're done in the private. That still helps us all enormously. If I would shut up now and go over it, it helps us all enormously, really. But second, if you really could meet me, I mean, you would like the class even less, maybe. You'd hate me even more, maybe. There'd be a lot bigger problems. But one thing you'd know about me, really, if you guys, is that I so deeply do not give a shit about wrong answers, like way more than you can know. Because I get things wrong much more than I do right. And it's not, and you cannot learn to, you cannot win a lot unless you really learn how to lose, like in science. I mean, so if you all could know, really, that it'd be better just to share these wrong answers and there'd be no shame in it, that would be great. But I know it takes a while to realize that. Anyway, I'm going to say now, so everybody, I'm going to start going over, because now at least I know, like, about 4 people got some answers. So now I'll be talking about something you're thinking about. Yeah, and people are having hard times with I know I'm like, yeah. Oh no, and even someone. Okay, I'm going to say one other thing. Someone in the private chat, very good. Like if class were the conversation that I seem to be sort of having in micro units with people in the private, then this definitely would be educational. Because right, like someone put in the chat, oh, I see how my answer's wrong because I used the wrong equation. But in fact, they had used the right equation. They even did use the right equation. And I'm going to show you all now. But it's easy to think that it's the wrong equation when you get swept up in units. So okay, at least now I'll feel like I'm doing something worthwhile when I show you all this. But I'm long way of saying thank you. Those of you who communicate in any way. What? Oh, yes. 1 second. 1 second. Hold on. Sorry. Okay. So I'm about to go over this every we have like, okay, we have like 20 minutes. I'm going to say, I know I didn't just suddenly make a class any more interesting than it was. This doesn't make a class any more clear than it was for any of you, but it does make it easier to do a better job for me. Now that about like 6 or 7 people really just heavily participated here, and I really appreciate it. It seems to me now, I'm going to go over these problems, and it seems to me you all get them enough that you'll follow me when I go over them. But you are misguided slightly enough on them, or like not totally clear on them yet, that it really is worth me going over them. And I want you all to know that if you tried this problem today and didn't get it, totally nail it, but then you totally get it by the end of the day, I need you all to understand that then we are progressing at the right pace. Like there's also too much always mania about pacing in classes in life, but then especially during this virus where like no one knows what the meter sticks are. Like, let me tell you, this is the way physics always works. If you thought honestly about this problem that I wrote down, and you know in your heart that you thought about it honestly, and you actually can't nail it, but then by the end of this class, you see how it is nailable, don't say to yourself, well, that's just one problem, I still don't know anything. Or don't say to yourself, oh my God, we're barely, like we're only on this topic of physics, like there's so many other topics we have to get to. Don't say any of, or when's the exam? If you didn't get it before today and you get it at the end of the day, then physics is doing the right thing, and you're doing the right thing by physics, and your grade will be right, and the pacing will be right. It's always just about getting the next thing. And now I feel like I know what the next thing is, listening to your answers. Okay, so I'm gonna go over this now, and then we're gonna part company, and all of you are just gonna work on whatever next problem you're up to in the homework, wherever that is, whether it was homework 1 or homework 4. I haven't assigned anything new in a while. I haven't given back anything in a while. Let's just all keep going one step at a time like this. But here we go. But I really appreciate every single one you that put something in the chat. Oh, also, yeah, as we progress, it might be easier for it to be not a series of private chats. Like, obviously, that does make it a little bit more tricky, but I totally understand. Okay. So we're going over these problems. Oh, the answers. Let me tell you the answers. Just for perspective, the answers are these. I'm going to work them out. Again, but just so that you can have some satisfaction or some clarity or whatever. Yeah, I think at the end of assuming I remember the questions correctly, that's supposed to be a L for miles. Like, and there's many different ways to do these problems. There's an infinite, well, maybe there's an infinite number, but of course, there's an infinite number of ways to do these problems wrong. There's an infinite number of wrong answers, and there really are right answers. These are the right answers. They can be expressed in other units, perhaps, but I think the problem even asked for what units it wanted them expressed in. So, all right. Now I'm going to go over the problems, unless anybody wants to share anything. Sorry about like, because many of you, by the way, gave me some answers in the chat that. Oh, well, okay, that's a really good question. Wait a minute. Well, so I'm just responding to the chat now. Okay. So the answer is 11 for the first one. Now in some ways, again, I just immediately got a couple of chats, which are totally cool and totally helpful. Again, it might be, but whatever. I just got 2 chats that tell me a couple of people just suddenly had an aha moment in their mind by virtue of seeing the answer. If you thought the answer was 22 miles for the first one, but you see the 11 and you're like, aha, oh, if something like went through your mind, like, well, wait, yeah. I mean, those aha moments that a couple of people have, I hope are legitimate. Sometimes aha moments can be deceptive, but I think a couple of people did have legitimate aha moments just now. Just understand, can you use the 1/2 AT squared equation to get this? Oh, most certainly yes. And that's what I will show everybody. You most certainly can. Like, in a way, these 2 questions that I asked today are just supposed to be practices in the 2 new equations, the 1/2 AT squared equation that we got on Wednesday, and then the v squared minus v naught equation. And it's true, the first one you can do with equation number 6, and the second one you can do with equation number 7. You don't have to do either one of them that way, but you totally can. But if you do use the equations, you do have to be careful about units. So let me say one thing. I'm talking about number 1 here. Okay, one thing I want to say very clearly, the answer to number 1 is 11 miles. I am going to do it out. I do not believe, I'm not saying that I have done it out yet today, but for some of the people that had the aha, let's just backtrack for a second. And remember, the only thing I've changed about today's problem, like from yesterday, from last week, is the actual number, but the whole concept of constant acceleration and free fall and all that is still the same. So if you look back to your notes from last week or from last Wednesday, and you look at the case where we call gravity its sort of customary meters per second squared number of 10, right? You can look back at those charts or equations or however you did them. And if you look back there, now this is going to be almost a trick. I'm warning everybody, I'm about to ask a question that you might regard as a trick. It certainly is a tricky question, but if you go back to basics of not miles and all that, but meters per second squared, and if something is dropped from rest, and accelerates at 10 meters per second every second, then how far will it fall in the first second? Like, I'm asking I'm asking like the easier version of today's question. And I'm asking to anybody, if anybody has the guts or the desire to either put in the chat or say, I'm saying and if you don't like the 10, if you want to call it 9.8, if that's what you remember better from lab or from high school or something, if gravity is 9.8 and you drop something from rest, if it's 9.8 meters per second squared, and you drop something from 0 meters per second, how many meters will it fall in the first second? let me put it this way. Please raise your hand if you hear the question. You don't have to answer it. Just raise your electronic hand if you hear the question. Thank you, Rachel. I totally appreciate it. It's a race. Yes, it's totally a race. Abby, yes, thank you. Ingrid, thank you. Yes, I appreciate it. And 4 more people raised in the, oh, how do you, I know 4 other people didn't, I can't see them for some reason. Oh, yes, thank you, Brian. Thank you, Heaven. I know this is a thank you, Wenyi. Okay, so you all hear the question, right? So the question is, from rest, how far does something fall in the first second? Now, I'm not trying to put anybody on the spot because I will admit this is a question that can trick you. Like if you, the answer is maybe obvious, but maybe not. So I don't want to put anybody on the spot and I don't want to embarrass anybody. But does anybody think they know the answer? And you don't, and you, again, everybody raise your hand if you hear the question. Or everybody raise your hand right now. Just raise your hand, please. I know I'm becoming good. Thank you, Kimberly. Thank you, Wendy. Thank you, Heaven. Thank you. Oh, 10 people. Good. Oh, a lot. Okay, Brian. Thank you. Thank you. All right. So you're all hearing me. Oh, Jamie. Thank you. I totally see you. Crystal. Thank you. Ingrid. I know this is so embarrassing. I'm doing this like romper room, but thank you, Rachel. Thank you, Elizabeth. Okay. It's going to be a thank you, Eileen. I totally saw you. All right. So you all hear the question. So the question is, if you drop something from rest and it accelerates at 9.8 meters per second every second, how far does it fall in the first second? Okay. I'm going to say the answer. So you'll know in your heart whether you understood that this was the answer or not, right? You never have to look me in the face on this because I still think this is hard. I still think it's okay to be wrong about this, but you got to know there's something that you're wrong about and get it right. So I'm going to say in the case that I'm saying right now of gravity being, if gravity is 9.8, then something falls 4.9 meters in the first second. If you call gravity 10, something falls 5 meters in the first second. Now, that may be totally clear from last week. That may still be, you might remember that seemed to be a punchline last week and still be fuzzy with it. You might never have heard anything and be shocked by that right now, but you got to understand that is a truth of physics and that you can't get anywhere farther in physics until we work that out. So I'm going to just say one last time. If gravity is 9.8 meters per second squared, then it'll fall 4.9 meters in the first second, okay? And that's because it speeds up from 0 to 9.8 meters per second in that second, right? Like it's speeding up from no motion at all the way up to 9.8 meters per second of motion. So on average, it's not always going 9.8. It's not always going 9.8 meters per second for that whole second. It's only going 9.8 meters per second right at the end of that second. And right at the beginning, it was going 0. It was smoothly building up the whole way. So on average, it was only going 4.9 meters per second. Therefore, in the second, it covered 4.9 meters, right? The logic always brings us back to average velocity is the point. But now here, for this problem, everything I just said is related, but it's not the end of the discussion. For this problem, then, yeah, if I were to say that the rate of gravity is 22 meters per second squared, then that would mean in the first second from rest, you'd fall 11 meters, not 22. That is true. But now there's something thicker to this problem though. I'm not saying that. I'm not saying that gravity is 22 meters per second squared. That actually would be a lie on this planet. That would be more true on something like Saturn or something. I'm saying that gravity is 22 miles per hour per second. And that's a unit that makes more sense in one way, but is harder to calculate with in another way. And I'm asking everybody, and this came up in the chat, okay? So going back to the problem I'm actually asking, I'm asking everybody, how far does something fall in the first minute, okay? Like I'm actually forcing you to make a decision about the unit. Like you have to make some kind of unit conversion somewhere because already 22 miles per hour per second is helpful in one way, but it's not consistent in another way. So you're gonna have to you would have to choose whether you're dealing with hours or seconds anyway, but then the question is asking not how far does something fall in the first second. It's asking how far does it fall in the first minute. Oh, and Heaven, I'm sorry, Heaven, do you have a question? Wait, or are you just raising it from before?
Oh no, yeah, I didn't unraise my hands.
Okay, cool. Okay, no, just making sure. Okay, so, okay, sorry. So this question is asking about a minute. So to be totally clear, the acceleration is 22 miles per hour per second. That means at the end of, in fact, let me write this down. Before you even do, so you can use this equation. Those of you who tried, you're right. It is practicing that equation, but you got to be careful when you plug in, just to make clear what the equation is trying to do. I'm saying like, if given this, if something speeds up by 22 miles per hour every second, and that is what I'm saying, like every second, is 22 miles per hour faster than before. I'm looking at the timetable, 15 minutes, right? What does that like mean in terms of charts or English or something? It means at t equals 1 second, the velocity has gotten up to 22 miles per hour, right? But that certainly doesn't mean it will have traveled 22 miles in that time, of course, because it hasn't, because first of all, it only got up to that speed at the end, like I was saying before, but also it 22 miles per hour means that if you give the full thing a full hour, it might travel 22 miles, but we've only been dropping for a second here, right? That's just a way of saying, so how far something's gotten in 1 second. You can't just like multiply 22 by 1, or even just to be totally clear, at t equals 1 second, I don't know how far this thing has fallen right away until I do some unit conversion or something, because even if I pick up on all the smart thing that I was trying to say before, that like it, you know, you wouldn't travel 10 meters in the first second, you would travel 5. Even if I get all that, still, that's all the wrong units. This thing after 1 second will be up to a speed of 22 miles per hour. So in that amount of time, in that 1 second, it has not traveled 22 miles, and it's not even traveled 11 miles, because it would travel 11 miles maybe in the first hour, not in the first. So what do we do? What do we do about this? We can plug in the equation if we want, but we have to be proper about the units. What we're saying is x minus x naught equals 1 half at squared plus v naught t. Okay, it's x naught, the original place where this thing started. I'm calling 0. I certainly can do that. And I can always do that. By the way, you could always, 0 is up to you. What you call 0 is up to you. It's most convenient always to call the place 0 wherever the object of analysis starts off. Wherever the object starts, call that 0, and then you don't have to deal with this term. That will work as long as you only have one object. If you have two objects starting different places, then you have to deal with this term, and that's really why it's there. But here it is 0, so I crossed off, made it 0. And then also v naught is definitely 0. This object started from rest. It did not, it wasn't thrown down, it was dropped. So we have x equals 1 half at squared is a shortcut of all the other equations that we totally can now use, and we are practicing it. But I plug in carefully with the units. I have 1 half 22 miles per hour per second times 1 minute squared. Like those are the facts. And when I look at that, and this is the thing, you have to write down units. Sometimes if you're lucky, like you get away with not writing them down because you know what's going on. But the reason sometimes people don't like to write units down is by writing units down, it actually shows them where they don't know what's going on. Like the minute I've written this now, like this thing here, this is correct. This is correct. And it's usable. I can go on from this now, but I know in my heart that most people looking at this, including me, this thing is such a mess. I don't want to deal with this. What I would do at most stages of my life in physics, if I looked at something like this, even though it is correct and I actually need it to go on, I would look like something like that and say, I cannot make heads. These units are a disaster. They're a mess, and I hate stoichiometry, or I hate unit conversion, whatever. Forget the units. I'll just cross them out and I'll just do the numbers. But that would just be lying to myself. I do have to do something with these units. The thing is what to do. Well, I'm going to start a new page. And I know this is like, well, it's boring. Everything is boring. I feel attention. But I cannot ignore the units that I'm being asked to calculate a motion of 1 minute. And yet the acceleration has been given to me in terms of hours and seconds. And when I just tried to show on the other pages, I cannot, that's a real reality that will change the numbers. So what if I do this? I'm writing the exact same thing again, but just so I have. Okay, I basically just wrote the exact same thing I did on the other page, except I didn't. I changed one thing. I made it clear to myself that both the hours and the seconds are both in the denominator. Like when I'm saying it in English, I like having the hours up top there, miles per hour every second. This thing is getting faster by 22 miles per hour every second. That's like how I think about it in English. But I got to understand mathematically, it's miles per hour per second. They're both being purred. They're both being divided. Both the hours and seconds are in the denominator. When I realize that, it's a little bit easier for me to deal with because now I'm just going to be careful and go one step at a time. I'm going to say, okay, I've got hours and seconds in the denominator there, but I've got minutes being multiplied. So I'm going to try to change everything to minutes now. By the way, let me say again, I know unit conversion is boring even on the most interesting of days. I also know that some of you got the wrong answer, then saw the right answer and said, oh, I realized what I did wrong. And it wasn't this, but like you're still satisfied that you just be careful because actually, please do copy this down anyway, even if you, okay, cool. And I'm seeing the chat. I totally appreciate, yeah. Like, right, and this is good because it is not, if everybody could really understand that physics is the most personal of sciences and it really is about each one of us and ourself or each one of us and our Lord or whatever, like I want to say to all of you, you might have, as soon as you saw the 11, you might think, oh, I get the answer now. And I still want to avoid these unit conversions. It was still because of some other mistake I made. No, like the units really matter here. It's like the whole point of the problem. And they're maybe boring, but so yes. So everybody watch this because you'll see even in the second part of this question, even when it looks like it all works out nicely, it's just nice. It's not, well, anyway. So what am I saying? I'm saying I've got hours and seconds in the denominator, but I've got minutes in effect in the numerator, right? I mean, it's like technically it's like minutes over 1, right? So I want to change these hours and seconds to minutes. I just go step at a time. Like first I'll change the hours to minutes, then I'll change the seconds. So I'm going to say, and I hope I have room for this, I'm going to say miles per hour times seconds times, I'm trying to change to minutes now, right? So times 1 hour over 60 minutes, right? Like whenever I do unit conversion, and I hated it until I didn't, like everything else in science, but most people with unit conversion, they're like, yeah, I get how to do it. And I know what the conversion is. Like I know 60 minutes in an hour, or I know, 1,000 meters in a kilometer. But what I always get, this is most people, including me, most people about unit conversion, the reason they hate it is first of all, they try to do too many steps at once. They'll try to convert 2 units at once instead of 1 because 1 is too boring, but you shouldn't do that. But second, they'll be like, I know the conversion and I know the process. I just never know whether to multiply or divide. I always get confused whether you multiply by the conversion factor or divide. A lot of people feel that way. Or what's worse is they don't even know they feel that way, but they feel that way. And so then they just like stop. What I'm here to tell all of you is always multiply. Just always multiply. In a unit conversion, always just multiply by something that equals 1. Multiply by the well-chosen 1. You're always like 1 hour is the same thing as 60 minutes. It's like X over X. It's the same thing. So it's 1. I always multiply. How do I know what to put on top and what to put on bottom? I just arrange it so that cancellations occur. Like I knew I was going to multiply by either I knew I was going to multiply by either 1 hour over 60 minutes or by 60 minutes over 1 hour. Like I knew that was my conversion and I knew it was going to multiply. I decided which way to write it by literally looking and saying, oh, I need the minutes to be left over. I need the hours to cancel. So I'll put the hours on top so they cancel with these. That's how to this day I always do unit conversions. I'm almost 50 years old. That's how I do them. I think it works. But so now I'm going to do it again too here. I'm going to say 22 miles. I'm going to say times again because I want to get rid of now that other. So I just got rid of the hours and turned them into minutes. Now I want to get rid of that seconds and turn those into minutes. So I'm going to say again, oh yeah, 1 minute equals 60 seconds. Like 1 minute is the same thing as 60 seconds. So if I put it over itself, it's 1, but I want the seconds to cancel. So I want the seconds to be on top. Right now, of course I ran out of room, but this whole thing, and I'm dragging this out because it looks easier than it is. But I'm literally, if you're really being strict about this and using the equation, what we're really saying is 1/2 times 22 miles per hour per second times 1 minute squared. In order to do that, I'm converting my miles per hour per second. I'm converting miles per hour per second into miles per minute per minute. That's what I'm doing, right? I mean, I've got, what if I did it correctly, and I did, I got rid of the hours, I got rid of the seconds, and I end up with 2 minutes in the denominator. I mean, minutes times minutes, which would almost be annoying and weird and would almost indicate that I'd done something wrong, except that A, it is an acceleration. So you're supposed to have squared time. You're supposed to have 2 time units in the denominator, but second of all, it's perfect because they're going to cancel with the minute squared that is called for by t squared. So it's really looking good to me. What I really have now is, whoop, is the wrong color. Now, this is an important step, and I know I'm looking at the time. We have like 5 minutes. This is the step right here. Wait, that's supposed to say a minute. This is where right here, in other words, something lovely just happened that wasn't a coincidence, specifically because there happened to be 60 seconds in a minute and 60 minutes in an hour, right? Like this wouldn't work with any other combination of somethings, like if you did days and years or something. Because there's 60 minutes in an hour and 60 seconds in a minute, then 22 miles per hour, what we've just, if you walk through this unit conversion, what you realize, and what's kind of interesting is that, oh, 22 miles per hour per second is an intuitive but not mathematical way of expressing an acceleration, like, or at least I think it's easier to picture 22 miles per hour of gain every second, right? It's easier to kind of say and picture, but it's not like the mathematically like legitimate thing of, or the mathematically convenient thing of time units squared. Well, if you do the conversion, it turns out that 22 miles per hour per second is equivalent to 22 miles per minute squared. So this makes it now like that unit. Like now we have time squared in the denominator. So now any model that we made with gravity now does apply. In other words, the whole discussion of, oh, if it's 10 meters per second squared, then in the first second, it'll travel 5 meters. Like that discussion directly does apply here. Yes, you can just transfer that thing into here. Yes, because I actually phrased the question as how far does this thing fall in the first minute? And it turns out that even though I wouldn't have known this right off the bat, we both multiplied by 60 and divided by 60 to convert the units. So what we get, so what we get as an acceleration rate is 22 miles per minute squared. And then yes, the minutes just cancel out and the equation returns what it should. The equation is just doing that thing of taking averages. That's why it's 1/2 of the gain in velocity. And so you get 11 miles. That is the answer. Okay, that's how it works. But you do have to account, and because it's 3 minutes left, I'll quickly do the second one. I'll race through the second. The second one, I'm literally just plugging in the other equation. So both of these could be viewed as plug-in chunks of the new equations, and we'll move. And that's it. There's no more equations for this chapter of 1D kinematics constant acceleration. But the other one, I just wait. The other one, yeah, we did this one. The other, yeah, we got that. The other. Yeah, so the other one was this one here at x equals 22 miles. What's v? What I'm partly trying to emphasize with this question, first of all, yeah, this is an example where time is not given and time is not being asked for. You could go step by step and say, well, how much, all right, at x equals 22 miles, by the time the thing is dropped 22 miles, like how much time has passed? It's easy to think, oh, I guess 1 second or 1 minute, but no. We just got through explaining all that. The amount of time that's passed by the time this thing does 22 miles is not 1 second or 1 minute. You'd have to figure it out. It's figure outable, but then you'd have to plug that into some other equation to get v, which is what the question asks. Or we could just go straight to the new equation, x minus x naught equals v squared minus v, like this thing right here is what I plugged into. And this is the equation for these kind of circumstances. I crossed out 2 zeros, so I have x equals v squared over 2a. Then my advice to everybody at that moment, and some of you may have gotten that far in the problem, that moment a lot of people would plug in numbers and then rearrange to get, I advise, especially as you feel stronger and stronger in physics or are bored and want a challenge, get in the habit of rearranging first and then plugging in the numbers. That's the best way in physics. That's what makes it physics, not math, actually. Partly. So I rearranged and I'm saying, okay, multiply both sides by 2a, v squared equals 2ax, therefore v equals the square root of 2ax. I'm just reading the stuff that's in blue here. So then I plugged in the numbers, but I'm careful about the units. I plugged in 2 and 22 miles per hour per second, and then I plugged in 22 miles. Now I'm looking for love in all the wrong place. No, I'm looking for V in the right place. I'm looking for V on the last line here. We're just about done. V says to be the square root of 2 times the 22. Well, V is supposed to be like distance per time. Like V has to be measured in miles per second or better miles per hour. But something per something, I think miles per hour is more natural because that's what the whole problem was presented it. So I have to convert these seconds down here into hours before I can go any further. I have to convert seconds to hours. So I'm going to divide this whole thing by 60 by 60. So I can have something that's miles squared over hours squared. That's what I did. So I multiply. Yeah, if it's going 22 miles per hour per second, but I want to convert that to miles per hour, I want to convert all to hours, then that means I'm multiplying by 60 and multiplying again, just for the reason I did before. So the seconds cancel and you end up with hours. And if you do that, you end up getting approximately 1,867 miles per hour, which is very, very fast, a lot faster than the speed of sound. But by the way, lots of things do go that fast. Airplanes can go that fast, and rocket ships go like 45,000 miles an hour. So it's not like impossible or anything. It's just very fast. But I've totally kept you. I think I really keep doing what you're doing. And whatever you're doing at home, just do the next thing. Wherever you are in the homework, if you're on homework 1, just do the next part that you haven't done yet. Just go back and see if anything makes more sense now than it did before. That's always only the goal. I'm going to rush right now because I have a thing coming in. So do you. I'll check email. I'll post all of this.